叫什么 no？ 下载。Hello。等一下。这样子。然后是黄国罗，抱歉同学，我测试一下。单一分页，这个，所以这样大家应该看得到。Hello， 大家听得到吗？可以，好。习惯一下。放大。OK， 资金没有出现。但是应该可以好。那样子，要直播，直播这边也要截取。视窗截取。有什么用？这样子吗？感觉可以。哦。然后大家，对 YouTube 不需要加入 ，YouTube 那边基本上是拿来做录音的。我们的 interaction 都会在 Google Meet 这边，所以大家应该都还能听得到。好，然后期中考卷我快改完了，我稍微拖了延一下。OK， sorry I should speak English. Yeah, so the midterm I almost finished grading, should be finishing in 1 and 2 hours. And sorry about that. But today we'll go over the solution. I think most people are doing very good here. We have lots of people that have over 100. Okay, and so maybe we'll, and I think it's maybe a bit too easy this time. I guess it's okay. We go over lots of basic here. Yeah, so maybe we'll also stop because earlier today, this will be a bit of test online teaching. Oh, it's really weird. I'm trying to, okay, let me try to set this up later. It's kind of weird. I am looking at my 2 monitors. Let's see, can I make this a little less weird? Oh, okay, this might be a little better. Like this. And this. Okay, okay. Zijing is here. Let's make him. How do I make you? Conference folder. Okay, like this. Okay, yeah. So midterm should be graded very soon. What's this? It should be fine. Yeah. It should be graded, and I'm not too sure about eLearn. I think we can upload the graded file to eLearn. Let me check eLearn quickly here, or Zijing can answer. all the graded history should be uploaded to Elearn, right? Should be able to. Anyway, and we'll go over the solution today. And as we said, made the announcement earlier, the interaction will happen in. Oh, it's really weird. Where is my Google Meet? Okay. Okay, the interaction will happen on Google Meet, and but we also have streaming on YouTube, and the video will be on YouTube. Okay, and, so this is how we plan to work on from now on. Okay, so let's see how long we need to go through the exams. So the first quadrant is pretty okay. Maybe it's okay. Yeah, the first quadrant is pretty straightforward. You calculate the Fourier series coefficient AK for two functions. I think it's a little mistake on my part. It's a little bit too easy. I want these two to be a little different, but they are turned out the same. So we have this x equal to constant plus sine and cosine. And this is one of the many examples we go through in class, where you have both sine and cosine, and you want to find the Fourier series or Fourier transform. You don't actually need to do calculation. You can just use Euler relationship to write sine and cosine in complex exponential. So yeah. And I guess only a little non-trivial part is you need to determine the period of those sine and cosine, and that's the part where it might be different for continuous time function and a discrete time function. So for continuous time function, period is just 2 pi divided by omega naught, where omega naught is whatever in front of your t here. So omega naught is 2 pi over 5 here, and t is just 2 pi divided by this omega naught. So you have big T here, and you can just write this as you can just write your x of t as summation of complex exponential. So this j corresponds to the constant term, and this sign can written as this e to the j omega t minus e to the minus j omega t, and obviously divided by 2j. And from here you can directly read all the coefficients. So you don't even need to do the integration in the Fourier transform formula. So the j here, so j for the a naught, and 2j, and plus 2j minus 2j. So actually plus 1 over 2j and then minus 2j, 1 minus 2j. And therefore a plus minus 1. And that's for all Fourier coefficients. So to be complete, you also need to say the AKs are zeros for all other things. And then let's go to the discrete part. So this is where I made a little mistake. So it's actually same as the continuous part. So remember, for discrete part, this omega to n, you need to be a little careful. You need to make sure n is an integer. N is already an integer here, so it's just the same. The period is also 5, and you write your x of n in the same complex exponential, and you can get excuse me. Then yeah, so the coefficients are basically the same, but for AKs, for other AK, so this A0, A plus minus 1 are the same, but for other AK it's a little different now, because for discrete time, we usually have our AK being periodic with the same period of as your x. So it's not all other AK are 0, AK are periodic. So for example, A6 here is going to be equal to A1. A6 here is going to be 0. Okay. So yeah, that's very basic. Any question? If not, Then let's go to the other one. Okay. And problem two is also pretty intuitive. It asks you to think about how a filter works. So we have a high pass filter here. It only pays a signal with high frequency, as we said here. So any signal with frequency less than 20 is going to be filtered out, and any signal with frequency bigger than 20 will stay. So if we draw a picture, it looks like this. Okay. So this is your big H, and you have plus 20 here and minus 20 here. So anything bigger or less than, and this is omega. So anything bigger than 20 or less than 20 states, and in the between it gets filtered out. And now we have a bit of logic here. So we say we make a signal getting this and filtered by this thing, and we want it to be stay the same. And and so what you want to do is you think about, now you also have a big S here, it's some signal, and you will know that when you apply a filter to a signal, it means that in a frequency domain they multiply each other, because the filter is, we think it as a LTI system. So filter out the big Y is big X times big H, and in the middle part it's going to become 0, right? Because so Y equal to X times H. Then if Y equal to X, then big Y also equal to big X, and big Y is going to be 0 in the middle part because H is 0. So X must start with 0 in the middle part. So yeah, that's what we are trying to get. And it's a little more complicated, that X is the periodic signal, and with fundamental period T pi equal 4. So if you, okay, so this is kind of a problem in chapter 3, but we can also think in terms of chapter 4. So it's a periodic signal, so its Fourier transform is going to be a few spikes. So the delta functions, if we write it in terms of Fourier transform, and now the distance between the delta function is going to be omega naught. Okay? Yeah. Because k omega naught is the actual frequency. And yeah, so we want to, so those spikes should be 0, so we know the k inside this minus 20 to 20 range should all be, so the ak correspond to those k in this range should be all be 0, and then it's pretty easy to do calculation. Yeah, so we have that k omega naught between this minus 20 to 20 should, those ak should be 0, and the omega naught, if you just calculate here, is 8. Then we know there should actually be a little more here. So there will actually be 5 here. Let me draw once again here. Okay. So it is 20 minus 20, then the Fourier transform is going to be like 5 spike. Because we know the omega naught is 8. Okay. And all outer thing is going to stay the same. And yeah, so those 5 spikes should be 0, and and yeah, so that's the answer. Okay, so it's a pretty intuitive question, just asking you whether you know what filter do. Any question? Okay, not. Then let's go to problem 3. We're going to finish very early. Okay. 3. Okay. So problem 3 is also very basic. So we have Fourier series coefficients for some signal, and it's like this. Is something looks pretty complicated. AK equal to e to the minus k squared plus jk. But we just want to check properties, and yeah. So this is just using whatever the thing we have in a table. So we're going to ask is x even or is it real, and you just want to check those properties on the coefficients. And so the things on the table we had, and we have go through this multiple times in all different forms of Fourier transform. So if x is real in a time domain, then on the frequency domain you must have this conjugate equal to negation in frequency. So ak should be equal to a star equal to minus k, and we check whether this relationship is satisfied by this. And that's true because if you get a star, then this j becomes minus j, and the minus sign cancel away, you also get a minus sign k. Yeah. So yeah, you just check the property, and you see that xt should be real, and it's even, and yeah, that's also check a property. You check whether ak equal to a minus k. And when you turn ak to a minus k, then you see a minus sign in this jk. So no, ak is not even. And then this question is a bit trickier. We want to get a time shift to make this even. Okay. And yeah. So first we apply the time shift formula. So x of t plus 1. It will just become you get a plus 1 here, then you get the extra e to the j omega naught k here. Okay. And yeah, and then you can just do the math. So have e to the minus k squared, e to the jk omega. So yeah, so the j omega k also go to the exponent here. So, and we separate into okay part and weird part. So it's e to the minus k squared part is going to even, so we kind of just put it outside because our goal is to check whether this function is even, right? Okay. And so I actually didn't make this quadrant very precise, so it's actually going to have many solutions. With more solution than I thought. So you want this to be even. So very easy solution is to pick omega naught equal to minus 1. Okay. So if omega naught equal to minus 1, then you are just left with e to the minus k squared, and this is an even function. So this is even, then your x over t plus 1 is also going to even. But there are quite a bit more solution here. Okay, because we have a periodic signal, so this k is actually discrete value. K is going to be integer, and yeah, so k is an integer. Then e to the jk omega naught plus 1 has chance to be even when this omega naught plus 1 is not 0. Okay, so we do this carefully. So we write this, once again, use Euler formula. We put this jk omega naught 1 plus this e to the jk omega naught plus 1 into the cosine part and the sine part. And now we know the cosine part is even and the sine part is odd. So it want this to be want this function to be even, then we want the odd part to always vanish. And that means sine jk omega naught plus 1 should be 0. Okay. And yeah, so this part needs to be 0, then this k omega naught plus 1 should be equal to, sorry, then 1, the inside will be like integer multiple of pi, and so k is already integer, and if this omega naught plus 1 is integer multiple of pi, then we succeed. So yeah, so omega naught plus 1 is n pi, then omega naught is n pi minus 1. So there are quite a few of omega naught satisfy this relationship. And okay, and I guess there's something a little more to say is, so technically this is not quite correct in terms of how we defined fundamental period. Okay. And I guess, sorry, how we define fundamental frequency. Okay, but I think it is okay and it looks better. So why do I say this? Because we define fundamental frequency as 2 pi divided by the fundamental period. And yeah, and the fundamental period is always positive. So if you go strictly by our definition here, then fundamental frequency should also be always positive. And yeah, so that means that by our definition, e to the minus j omega t, okay, fundamental frequency usually omega naught instead of minus omega naught. Okay, and what that means here is that if we go by the strict definition, the fundamental frequency is actually absolute value of pi n pi minus 1. But yeah, but that's, in terms of mathematics, that's quite, how should I say? That doesn't seem very good in combination of other things. So this answer is also pretty nice, because you get an extra, yeah, if you get an extra absolute value sign here, and it gets very annoying when you plug in other formula. So we also accept the answer of fundamental frequency being negative here, because it's actually easier to use when you try to combine the other part. You don't get an arbitrary absolute value here. Okay. So any question? It is quite involved here. Maybe next year we'll have asked you to give all the answers. Here we are not very specific about how many omega naught we want you to find. Yeah. So any question about this problem? Okay. No? I think most people do pretty good on this problem. Let's see. The data we have here. Yeah, seems okay. Maybe Zijing want to say something about anyone. Okay, I guess no. Okay, then next one. Then problem 4. Problem 4, we got some people doing this wrong, but I don't know, I think this is pretty straightforward. And we have similar example in the class, so I think it should be okay. I'm not sure, I kind of a little forgot we have similar things in homework, but I think we also have similar in homework. But anyway, this is one of the detective work question here. And the thing about this kind of problem is you want to solve for all the Fourier coefficients. Okay, so we are given a whole bunch of clues, and what we do is we using them to solve for what are the AK. And then we can answer what is the time domain. Well, actually these 3 times, so what are x of n. Okay. And so we look through this, and the easiest one, the biggest part is probably this one actually. So the second one tells you that xn is a periodic with a period n equal to 3. So it's a periodic signal, and you should do, then it's like chapter 3, and you should look for the Fourier series coefficient ak. And for this n equal to 3, now you need to remember that the discrete time with the period, then its Fourier series coefficient will have the same period. This ak will also have the period n equal to 3. So there are only 3 of them that are non-trivial, because it's going to repeat itself, like because it's going to be repeating themselves with a period of 3. So there are actually only 3 independent variables here, so a minus 1, a 0, and a plus 1. Okay, and sorry, a plus 1, and then there is going to be a2, and a2 is going to be equal to a minus 1. So you don't really need to solve for a2. So there are only 3 variables, and we already told you, just told you straight that a0 equals 0. So this is 0. Okay. And then we have this energy in the time domain, and it's already in a very obvious form to tell you that you should use the Parseval's relationship. And so that will tell you that the sum of a1 absolute square and the sum of a minus 1 absolute square, so the sum relationship between them. And finally, you can use those two relationships that a1 is positive real and an is real. Okay? And a1 is positive real, well, that tells you this is positive real. And then x of n is real, give you this. Okay? And as always. And if you plug in that for the a plus 1 and a1 minus 1 pair, that shows you a minus 1, so it's minus k, so you have k equal to 1. A minus 1 equal to a1 and complex conjugate. And a1 is real, so that just means a minus 1 also equal to a plus 1. So now you also have those two variables equal to each other. Now you only have one variable. Therefore, this equation tells you about what it is. And if you solve it, and you just get a1 equal to 1 minus 4. Okay. And once you have that, then x of n is totally specified. You already know the Fourier series coefficient. So you just use the formula of x of n equal to summation ak e to the j omega not k n. Okay, and yeah, and you get that. And so there are 2 terms, so the plus 1 term and the minus 1 term, and you can find out that they can return in terms of this cosine. Okay, and read here ABC. And some mistake here, I think one is somehow people do mistake in this elementary arithmetic. Somehow, yeah, the division you get it wrong. That's just wrong in calculation. And the biggest problem is this part. So we ask you to show this. You cannot use this as something given to derive your answer. Okay? Although sometimes it's good to work your question backward, but you want your derivation to have the correct, what's that called? Correct causality. So like correct flow of logic. You want to use those relationships to derive this. You cannot just assume this is true and solve for ABC. Okay? You need to show that this form is actually is actually something you can get from all those relationships. Okay, so some people, so you just say that xn equal to a cosine bn plus c, then try to solve for ABC. That's not correct because you are skipping things like x is real. You actually need to solve for the xn and show that it's this form. Okay, so that's the biggest mistake people make. And some people are just clueless about this. I think you need to study more because this is quite a standard problem that we have in our class example. Okay? And yeah, I think someone asked me whether only need one answer, so it's actually pretty strict form. I think A and B are really something you cannot change, and you can change C to like some plus 2 pi, but doesn't matter. Okay. So any question on problem 4? Well, we're actually speaking very slow. Maybe the time will be about right. No question? Okay. Then problem 5. Okay, so this is so we have 2 examples of Fourier transform here, and this has gotten more mistake than I expected. So we have a very basic one is kind of similar to problem 1, where you have sine function and you want to find its Fourier transform. And there are many ways to do this. And here we have kind of brute force integration, but not quite. So because you have this exponential integration, and we don't actually quite know how to do. So I guess the easier way to see this is we have this 2 sine equal to so this we can once again use the Euler relationship and write sine instead of complex exponential. The 2 sine is okay. Let me see if I can do this correct. So this is equal to okay. This thing 1 over j and e to the j phi t plus 3 minus e to the minus j phi t plus 3. Excuse me. Minus t phi j plus 3. Okay. And then you can do Fourier transform on those 2 things, and then you use so now you just have the plus 3j and the minus 3j here. So when you do Fourier transform on this thing, Fourier transform, then you get 1 over j and e to the 3j, and the Fourier transform of this e to the phi j phi t minus Fourier transform of e to the minus j phi t. Okay, so that's basically what happened here. And those complex exponential Fourier transform you can look up in the table, and that's going to give you 2 pi delta function and 2 pi delta function. Okay, so that's kind of the brute force way to do this. And I guess the way I designed to do this is you can it's very similar. So you look at this and you also write this, and you can also think this as a Fourier series. And no, I guess that's the same. Yeah, you can think about the Fourier series, and so you write this as summation ak. And yeah, so you think this as Fourier series, and you see the Fourier series coefficient is this e to the 3j. Oh, I get this wrong. So it's actually the so it's actually e to the 3j here and minus and e to the minus 3j. Okay. And you can also think this this part as Fourier series coefficient, and this part as the Fourier series coefficient. And then go to Fourier series to Fourier transform, then get this HR 2 pi delta function. Okay, and so that's one way to do this. And another way to do this that many people do, but actually it's quite hard to do correct, is you start with psi. So you have a Fourier transform of psi phi t, and it's going to give you this delta omega minus phi, delta omega plus phi, and then use the x of t minus t naught time shift to get this plus 3. But now this t naught is not 3. That's what many people get a mistake. Okay? Because, yeah. Because it's psi phi t plus 3 is actually psi phi and t plus 3 over 5. That's the correct way to do this. Okay? So, yeah. So if you use time shift, then you need to actually shift by 3 over 5. And if you don't, then you made a mistake. Okay. Or you want to do this shift by 3 first, then shift by 5. But if you shift by 5, you are going to get really weird. You are going to get omega divided by phi and another 1 over phi outside if you go use the time shift formula. And if you are smart, you will, or you know delta function well, you know you can actually get 1 over 5 and outside phi cancel out. But if you don't, that's also okay. Oh. Yeah. Okay, so that's this. And any question? Alright, it will actually be a little faster. Okay, and the next one, then we have this t function. Okay, and so it's kind of a polynomial function. So the function look at this is t between 1 and 0. Sorry, between -1 and 1 and 0 outside. And yeah, it's a very finite function, so you should be able to get its Fourier transform. And once again, there are many ways to do this. And here we give the most brute force way. So we just do the Fourier integral here. And the range is going to be -1 to 1. And so your function times the complex exponential factor. And to do this integral, there are also two ways. One is kind of how you deal with Fourier transform too. If you are a physics department, then you will know the Feynman trick. You can think about this as like if you do the integral of -1 e to the minus j omega t dt, and then get the partial derivative of omega, then you are going to get minus j omega -1 to 1 t to the minus j omega t dt. And yeah, so you can get this from doing this and divide by j omega. Okay, and sorry, not the omega, and divide by this minus j. Okay, and that's like using the differentiation formula in the Fourier transform. So that's one way, and yeah, it's very noisy, so let's erase this. Yeah, but here we do another trick to do this integral. That's integration by part, and yeah, that's something you need to remember in calculus. So integration by part, you think this is u and this is v prime, and so you have a u dv. You think this is u and this part is dv, and so you have a uv minus v du. Okay, and so your u is 1 and your v is -1 over j omega is equal to minus j omega t. And then you can get integration by part and do the calculation, and you get the cosine term and the sine term. So that's the first way, and just do brute force calculation. And the second way to do this is, I guess the easiest way is kind of like when you do the Feynman trick on this omega. That is, you use the I didn't have it show here. Anyway, you have the differential property on the Fourier transform, right? So first we know that how the square function. So this is something you can look up in the table. So if we have -1, 1, and this thing. And this is going to give you some, if you do Fourier transform, this is going to be like sinc, like sine omega over omega, and I think there is a 2, not sure. But anyway, so this function, and you want, so, and you see, so it's called is g of x, and you see that our x of t is t times g of x, and if you do, so you do Fourier transform pair, then that should be d big G d omega, and I think there's a J somewhere, J here, yeah. So yeah, you can also use this relationship, and so basically you do a differentiation on this sine omega over omega, and you can get your answer. And finally, there's a third way to do this, that is you use the integration formula. Okay? Because you can look at this x of t and you think it's very similar to the integration of this thing. But that way is very prone to get error, because you want your x of t to, okay, let's say, because it's actually not integration of this thing. Okay, you need to be very careful. X of t need to be integration of minus infinity to t, or some h of t dt. And h of t is not going to be this thing, even though you think the constant integration is tan. But if you integrate this thing from minus infinity to here, then you start with 0. But you actually start with -1 here. So this h of t is actually look like you actually need 2h delta function. Okay. So h of t actually is this thing, but your x of t start with -1, so you need a -1 delta function here, and another +1 delta function here, because this thing also drops to 0 here. Okay, and if you use this h of t and use the integration formula, so 1 over j omega something, and like some x of 0 delta function thing, that's the integration formula. With this h of t, then you can get the correct answer, but it's very prone to error. 第5题 B 的答案，你看起来那个是错的，因为有一个 cosine term 跟一个 sin term。你可能是用到了我刚刚说的这 integration formula， 或是或是你可能直接计算错误，就是这里很多正负号的东西可能会算错，但是你写那个看起来不是对的。分布积分的话，我好像有看到，但是应该是分布积分的时候有一个符号算错了，就是应该要有一个 sin 的部分，一个 cosine 的部分，所以如果你只有 sin 的话，你就算错了。OK， 分布积分的话，这里还蛮容易少一个符号的，你可以 check 一下。Okay. Any other question?这样子有回答到问题吗 ？Okay. Then, finally, next question. Next question, everyone do pretty well. I guess it's pretty, because it's really standard. Some people make mistake. I don't really know how you make mistake. And yeah, so it's very standard. So we solve LTI system. And system function. So basically you do Fourier transform on this thing, and you get a whole bunch of j omega here. So you will get those j omega times big Y on this side, and this 2 times big X on this side. and you move things around, then you find out the sixth function is big Y divided by dx, and then basically just read here the 2 and j omega squared 5j omega plus 6. And you want the impulse response here, and you want to do inverse Fourier transform of this thing, and you can do this easily by doing the partial fraction expression and break into those two things, and yeah, then you do inverse Fourier transform. It's getting very annoying here because we are recording, so let's really erase this. Sure. Maybe I'll have 纸巾 write in other ways in the solution later. Yeah. So you do the inverse Fourier transform and you basically look at the formula. Yeah, and 2 here, so -2, 3 here, -3. And the third part is very similar. So you have small x equals this thing, and big X is still this exponential decay, so just 1/4 plus j omega, and then you multiply, then your output will be, so the big Y will be big X times big H, and that's just similarly you get another whole bunch of rational function, and you can do partial fraction expansion again. And if you don't make a mistake, you get 1 minus 2, 1 here, and you get 1 minus 2, 1 here. And I think the only reasonable mistake here is people forgot the u of t here. So yeah, you should remember your u of t. It should be very straightforward question. Any question? Oh, also, there is something I don't realize how people make a mistake. So on problem 4, some of you try to distinguish whether x over n is even or odd. And yeah, I'm not sure how you get to that. There's nothing asking about whether x and n is even or odd. You just answer for x over n. Yeah. So that's very weird, but I guess I don't really know how to say. Anyway, so that's problem 6. It's very straightforward. You calculate everything in frequency domain, and you do partial fraction expansion. So when you transform it back to time domain, you just need to use this formula, the relationship between e to the minus at u of t equal to 1 minus a plus j omega. And yeah, so just go back and forth between time domain and the frequency domain. And then remember, the output of the entire system in time domain is just multiplication of system function and your inputs in frequency domain. So yeah, it's about time. So any question? Otherwise, I'll stop today and finish grading soon. No? Okay, then I guess that's it. Hope everything is okay. Let me stop now. Let me stop the YouTube stream first.